All right, so let's look at the properties of gases. So let's understand that this stuff, the ability to expand and fill the containers, being fluid, low density, being compressible, able to effuse and diffuse, this comes from the structure of the gases. At the most fundamental level, what separates a gas from a solid or a liquid is that distance between the particles. So solid or liquid, the particles are right next to each other, they're in contact. Gas, there's space in between them. And that's what makes all of these things possible in terms of changing shape, being able to flow, all this sort of thing, is that space in between the molecules, particularly the compressibility. Because there's space, they can push together more or allowed to drift further apart because of that space that's already there between the molecules or atoms or whatever the particles are going to be for the particular gas that's being considered. So note the definition of diffusion and effusion. Diffusion would be like the spreading of gas molecules from one place to another by random movement. Effusion, gas escaping through a hole into a vacuum, again through random movement. So these things are descriptions of the behavior of a gas. Now, one of the big things we measure about a gas is its pressure. So we have to understand that gas, like all molecules, vibrates and moves at any temperature above absolute zero. And in this case, what we're seeing here, because it fills a container, and that container is subject to all the forces of the laws of physics, what that means is that, well, gases are moving, they're going to bump into it, and even though each individual tiny atom or molecule or particle is an itty-bitty little thing, add up all of the huge number that's in there, and you're going to get a lot of force from together, all those particles randomly bouncing into the side. That is pressure. And the more particles that are in there, the more particles bouncing out the side, or again, more particles bouncing against the side, that's more pressure. So more gas tends to produce more pressure, which is not too much of a surprise. If you pump air into a tire, the pressure increases because there's more gas particles bumping against the sides of it. So that pressure is defined as force divided by area, which is why if you do something like this, compressing it to a lower volume, you are making this a smaller number, and playing with the calculator reveals that if you take the same number and divide it by a smaller number, if you decrease this, the final answer increases. If, on the other hand, you were to expand it, go from here to here, this makes this number go up. Sorry, this makes this number go up, and then what that does is it produces, divided by a larger number, a smaller result. So that's kind of the idea. Divide by a smaller number, bigger result, which is, say, bigger pressure in a compressed space. Divide by a smaller number, smaller result, which is less pressure in a larger space. So that's kind of the idea of what this is all about. If you decrease the area by squeezing something, you're making this number smaller, which makes this number bigger. After all, one can get the idea. Imagine holding a 5-pound weight in your hand, and then imagine having a 5-pound weight balanced on the end of a needle on your hand. Putting all that force in a much smaller area is going to get a very different result from just holding 5 pounds evenly spread all over your hand. So as far as these other things go, so the measuring of the pressure, this brings us to the idea of the barometer. This is not a test question. I don't care if anyone can remember or not remember the name of the dude who invented it or what year. We care about understanding what a barometer is and how it works. So first of all, let's understand the most basic version of a barometer, which is what this guy put together. It involved taking a meter-long glass tube. So here's a meter stick, gets roughly the idea. Imagine if it's a glass tube, like a giant test tube, closed on one end, open on the other. You fill it with mercury all the way up to the top, and then you plug it like this. And just like it shows here, you then take your glass tube and, oops, don't let it all fall out like that. So you put it down into a bowl of mercury, release, and now you have it in the mercury. That's actually the mercury. All of this would have quite a bit of weight to it. It's a very dense substance, and the weight of all that mercury would cause it to just pull down with such force that it actually leaves a vacuum up here. So that's like a lot of weight of mercury. You're talking quite a number of pounds of it in here. And the size of that vacuum turns out to be surprisingly constant. and tells us a lot about the pressure of the air outside, because here's the thing. Okay, so the mercury slides down a little bit, but of course a vacuum is not going to allow it to slide it all the way. It's really hard to create a vacuum in nature, so there's going to be a lot of tendency for that mercury to go back up into the vacuum. So it's only going to go so far. And then we can look at how high that mercury is, though, and determine the pressure. Now, why does that work? Why is mercury up here in the tube? Why does it not just drain all the way out? Well, the answer is, when you look at it, you have to consider the fact that, first of all, there is something pushing the mercury down into the bowl and up into the tube, and that is air pressure. And air pressure, if it was balanced with air inside the tube also pushing downward and pushing outward, would see, yeah, the mercury potentially draining out, especially if there was like a hole in here allowing air to enter in the top. But there is no air pressure in here, so there's nothing pushing the mercury down or allowing it to fall. However, air is pushing down on this bowl of mercury, pushing the mercury up into the tube and all the way into here, and it would love to push it all the way up. It's just the weight of the mercury is so much that it pulls it down, and that contest between air pressure pushing up and mercury's weight pulling it down leaves a vacuum of about, in real life, it's about 25 centimeters size. Now, the thing is, air pressure, like I said, is what pushes the mercury down into the dish and then up in here. So the thing is, the more the air pressure, the more the mercury gets pushed up into the tube. The less the air pressure, the less the mercury is pushed into the tube. What that means is that this becomes a way of measuring the pressure of the air outside. On a mountaintop, for example, where the air pressure is less, there's not as much force pushing the mercury down, and it can sink further because there's not as much force pushing it up into the tube. Say on the bottom of Death Valley or some other place where you're below sea level, the pressure is greater, forcing the mercury further up the tube, so it's going to rise higher. And so if you've ever heard about a weather report talking about the mercury rising and the mercury falling, it has to do with this barometer is used to measure the air pressure, which can give some indications of what the weather's going to be. So the air pressure does change. This is one of the units of measurement of pressure. And depending on the weather, yes, air pressure can rise or fall a bit. And if the air pressure rises, the mercury rises. If the air pressure falls, the mercury falls. And that's how we measure the pressure of the air using this barometer. Okay, I did mention that that pressure varies with altitude. I was saying that the higher you go on a mountain, the less the pressure. And that's kind of what this little thing is getting right here, this little animated picture. The idea is that we humans, living down here on Earth's surface, live at the bottom of an ocean of air. The air goes up hundreds, maybe, I think like 1,000 miles or something like that, just way up. And all that air is pushing down on us down here. Well, if you go up a mountain, there's not as much air on top of you, so it's less pressure. So this little graph is showing like the pressure like at sea level, and then as you rise, the atmosphere pressure, or as you go up in altitude, the pressure drops. So actually, I totally misread this one right here. Your altitude, sea level, down here, the pressure's up here, and the higher you go, as you rise in altitude, less pressure, less pressure, less pressure. As you rise in altitude, less, 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 less. 99% of the atmosphere is down here. I think it's below the 10-mile mark. The troposphere is home to 99% of the atmosphere. It's just this little piece. This is all atmosphere up here, but it's so little air, especially once you get up to the top reaches of the stratosphere. If you were up there without a spacesuit, it would feel like being in outer space, even though there actually is air up there. The space station is actually up somewhere, I think, in the thermosphere, which is up here, where there actually is technically inside the Earth's atmosphere, which is why over time it gradually slows down because it's bumping into the tiny amount of air molecules that are up there. So like without occasional boosts, it will eventually fall back down to your surface. So measuring pressure. Okay, so how do we measure the pressure at this? We have to consider there's different units. Now, one of the units you saw right here, but there's various others too. So one of them is the standard atmosphere, the average of what pressure tends to be at sea level. So we call that 1 ATM. And one standard atmosphere is equal to these other things. Now you saw torr earlier. One standard atmosphere is 760 torricelli, which is actually the same as this thing. It's actually, these two measurements are equal. This is millimeter of mercury, torricelli. or actually maybe it's torricelli, I'm not sure, I don't speak Italian, but regardless, these are equivalent units. Whatever this is the same number. So let's see, the SI unit, the Pascal, 101,300 pascals, that's, you'll notice this right here, it's a 4 sig fig number, as opposed to these, which are considered infinite sig figs, they are definitions. Also a 4 sig fig number, the kilopascal, because this is a little bit long and awkward number to work with. This is a little easier, nicer looking, and then we Americans tend to like pounds and stuff, so here it is in American, pounds per square inch. So 3 sig figs, of course, rounded for your convenience. The real number is like pi, goes on forever. But anyway, this is the units that you'll be using in our various equations. So although it is not necessarily required to memorize them, one should be familiar with them and be able to freely convert between one unit and the other unit. Okay, and these are examples that anyone should be able to do. Now these, it's not necessarily necessary to do these right now because there's a worksheet that covers the same function, so now is a good time to stop the notes and work on the worksheet that covers this. Or potentially, I suppose, want to work on it later, but regardless, it is important to make sure that to be able to do all of these easily and interchangeably, convert from one of any of these to any other of any of these. Okay, now if we're going to move on, let's deal with, okay, how do we actually put these to use, describing the properties and behaviors of a gas? So we need to do what's called, deal with what's called gas laws, a mathematical treatment describing how they behave. So, pressure and volume. Okay, we just dealt with the volume, with the units of pressure. Volume, we will also have to deal with that, but it'll be a little less, there's not as many options as what, liters and milliliters just about. Now, when it comes to pressure and volume, this right here is referring to what this guy noticed. So, you know, there is a unified gas off with all the gases, but it came from various individual observations by various scientists over the years. As one can see, this is a long time ago. And this is one of the first standards or scientific treatments in the modern sense of coming to understand the mathematical behavior of the properties of a gas. And he noticed this inverse relationship between pressure and volume. That means higher pressure, less volume. So more weight, it shrinks to a lesser volume. Less pressure, which less weight, and it expands to a greater volume. He noticed this about the behavior of gases and graphing that relationship. Greater pressure, less volume. Less pressure, greater volume. Right, so this was noticed. And so he also noticed that when you graph it out, you could take any pressure times whatever volume it had at that pressure and it would come out to this constant K. And if you change the pressure, and once it's set up to a new volume, you get that same constant K. So, okay, so considering all this, that like you can never squeeze it all the way down to 0 volume, but you keep close, because increasing the pressure reduces the volume, decreases the pressure, increases the volume, whatever. He noticed all this. He said, okay, if this K never changes, then this number is equal to the same number that this number is equal to, which means this is equal to this. And this is the version of Boyles Law that's used to describe the property of a gas. So you can start at a certain pressure and a certain volume. If you change the pressure, what's the new volume? You know, that's kind of the approach you can take to dealing with this sort of a thing. And by the way, a little side note, why does the volume never reach 0? Well, first of all, we have to consider that gases are particles. And if you squeeze enough particles together, they can't get any closer because they're finally physically touching. This is why the gas particles never reach a volume of 0, because they have a volume. And once they're all together, they can't. Once they're physically touching, they can't get any closer together. So whatever volume that represents of them all forced together into basically what's almost like a solid state, that's the volume they're going to be. And so it cannot get any smaller than that. It's a finite volume. Nothing has a volume of 0. All right, now having said that, let's look at what this looks like when you do an actual calculation. So a gas and container occupies a volume of 1.0 liters. if the pressure on the gas is increased from 1.0 atmospheres to 4.0 atmospheres, then what is the new volume? So whenever you see a question, you'll see just this. It's not going to tell you this. It's not going to tell you this. And by the way, I should also mention, you do not need to memorize that this is called Boyles Law. It is totally not necessary to match the name to the equation. What is necessary is to identify, because there's going to be other laws, there's Charles's Law, and Guy-Lussac's Law, and the ideal gas law. It will be critical to identify which gas law is appropriate for which question. So in doing so, you're going to say, okay, a volume, a pressure, and a pressure. So we're going to say this only has volume and pressure, so we're going to use the gas law that involves volume and pressure. So what you do then for this particular thing, what I'd like to see in terms of solving it, it's necessary first to write out the equation you're going to use. So write this out. Then identify what each of the variables is. Now, what's 1 and what's 2? How do you know that pressure 1 is this? Why is this not pressure 1? Why is this not pressure 2? We're going to say number 1 is where you start, number 2 is where you end. So let's see. A container occupies a volume of 1 liter. If the pressure on the gas is increased, so we've changed from this to this. So this means from this, that's P1, to this, that's P2. Then what is the new volume? Well, new volume, that means V2. Okay, so that's how I figure out that this is V1. Because the new volume is V2. So that's the reason why V2 is the question mark, because what is it? P2, 4.0 atmospheres, P1, 1.0 atmosphere, volume 1, 1.0 liters. Oops, there it is. Okay, now, having gone through how you identify that, here's the actual way to deal with it in a calculation. You simply, you've got your original equation. I want to see that on your work. Rearrange the equation with no numbers. And here it is written again. And by the way, just to be clear, how do you get V2? Divide both sides by V2. That cancels, so P1 V1 over V2 equals P2. So P1 V1 over P2 equals V2. So, oh, whoops, I just realized I totally showed you the wrong thing. Okay, so for solving for V2, you need to get V2 by itself, so that's P2 divided by P2. Those cancel. There you go, that's a little better. But, okay, so V2 equals P1 V1 over P2. So that's the math behind it in terms of what you actually do. It's simply a matter of rearrange it, plug in the numbers, and solve. So that's what I'm going to want to see from anybody doing this on a test is the original equation, rearranged equation, numbers plugged in, solution. I guess one should technically box the answer, but that would be your new volume. Okay, and now, just to be clear, it didn't ask how many liters is the new volume, it just said what is the new volume. So because it gave you liters, you respond with liters. Okay, it's a matter of simply responding with the units given. Now, one of the other things to point out, what if this had been given you milliliters? What if it had said milliliters? Well, consider what happened here. Notice that atmospheres cancel atmospheres to leave liters. So had it been milliliters, your answer would have also had units of milliliters. So unless it gives you one unit and specifically asks a different unit, it's oftentimes not going to be necessary to do any volume conversions on this sort of thing. But do pay attention in case it does ask you for a unit different from what's given or something like that. Okay. So these are the homework questions one can work on, and I would say at this point it's a good idea to pause the video and work on the example questions that, I'm not sure if they're like this or identical to this or whatever, but work on the questions that go on the worksheet associated with this. Okay, skipping ahead. Okay, Charles's Law. Again, I don't care if you can match Charles's Law with the equation that's going to come out here. I don't care about that. It doesn't matter if you remember like his name, when he lived. Those are not science questions. Okay, but let's go over what this thing represents and what it means and the variables and what the meaning of the variables in there. So first of all, this guy noticed these things happening. Let's see, do I have the, okay, I don't have any animations for this one. Increasing temperature increases volume, decreasing temperature decreases volume. And this is something that is perhaps not too much of a surprise to us modern people, particularly if you imagine like a balloon out on a hot day getting a little bigger, that sort of a thing. But under careful scientific experimentation, you can get some pretty good data showing that if something warms up, it gets big. Like a balloon should theoretically get bigger if it's out in the sun, or if it's out in the cold, it should theoretically get smaller. It's actually kind of cool if you put in liquid nitrogen, it shrinks like super small. Because you have liquid nitrogen being like really, really cold, it shrinks a balloon real small. Now, derivation of Charles's law. Okay, here's what the guy did. He noticed that the colder it gets, the less the volume, the warmer it gets, the greater the volume. As in higher temperature, greater volume, lower temperature, lower volume. So he said, all right, at any temperature, the volume and temperature that go together at that in those conditions, if you divide, they equal a particular constant, increase the temperature or decrease whatever, change the temperature, you get a different volume. Divide volume by temperature, you get a constant. These are equal to each other, so this number is equal to this number, which means effectively this is equal to the same number that this is, which means these are equal to, which means this becomes the version of the equation that you solve with. So again, doesn't matter if you remember this is called Charles' law. The questions will never ask you use Charles' law, whatever, that sort of thing. It's just going to say, it'll give you a scenario, and you have to decide which law is the best law to fit it. So one thing to mention about this, okay, volume and temperature, Kelvins only. Okay, why? Let's see. Let's consider why. I was looking for it on here, I don't see it. So consider if you have Celsius. Celsius can be zero. Zero is the freezing point of water, and it can get colder than that. So you can have negative temperatures. If you plug a negative temperature in here, and you solve for maybe one of the volumes, if you have a negative temperature in one of these and a positive temperature in the other, which is totally possible because you can raise the temperature from negative 10 to positive 10, for example, then you'd have one temperature negative. That'll mean whatever answer you get, it's going to be negative. And you could theoretically solve for a negative volume. That would make sense. You can't have a negative volume. So you're going to convert to kelvins because Kelvin is same as Celsius, except with the zero, instead of being the freezing point of water, the zero is absolute zero, so that no negative temperatures are possible. And as long as you don't have any negative temperatures, you won't get any negative answers, and that's what will make this equation work, because you can't have negative volumes. That's just not possible. So in a moment, I'll remind how to use Kelvin, but regardless, temperatures, if given for a question like this, will be given in Kelvin. So here we have temperatures given in Kelvin already. As a reminder, if you have degrees Kelvin, that's equal to degrees Celsius plus 273. So if you're given a degree Celsius, you have to add 273. Degrees Celsius equals Kelvin minus 273. So 273 is going to be the magic number here. So if you take a Kelvin, subtract 273, that's your Celsius temperature. If you take a Celsius temperature and add 273, that'll become your Kelvin temperature. In this case, you don't really need it's already given to you, but there are many cases when it is necessary. So anyway, let's get into dealing with this one. Now, be aware, I've given you this, but don't expect this to be given to you paired with a question like this on an actual test. You have to look and say, a volume, a temperature, a volume. Or a temperature, sorry, it's not a volume. So volume, a temperature, and then it says pressure constant at 1.0 atmospheres. If it says pressure is constant, this means ignore. You ignore stuff that's constant because it's not changing and it's not affecting your things. Okay, at least when it comes to ignore when it comes to problems where stuff is changing. So you ignore, if something is constant, you ignore it if other things are changing. So, okay. Now, how do we know it's changing? Because it talks about new volume, and it talks about cooling, which means a change in temperature. So you have temperature that's changing, you have volume that's changing. So you'd have to think, what's an equation that involves temperature and volume? And you'd have to reach back in your memory and pick this out. So then once you have that, the process becomes the same. Identify your variables. So we're going to say, two temperatures. It's cooled to this. So this is going to be either temperature 1 and temperature 2. This is temperature 1 or temperature 2. If you cool it to this, when you cool it to 278, that's what you end up with. And if that's what you end up with, then that must mean what you started with right there. So if you cool it to this, you went up here, which is why it's temperature 2. New volume, that would be V2. And if that's new volume is V2, then this must be V1. So that was, so 1, pick out your equation. 2, identify your variables. And so this is the same as I just did. So you get this down. So now you know you're solving for V2. Now you can rearrange to solve for V2, which means you're going to multiply both sides by T2. So times T2, so they can cancel, and times T2, giving you this equation, T2 times V1 over T1 equals V2, like that. And then once you've done that, you simply plug in the numbers and solve. So there's our temperature 2, temperature 1, volume 1. Notice Kelvin cancel Kelvin to leave liters for the answer's units. And since all it asked for was volume, a new volume, you reply with the same units you were given, liters. So that works nicely. And so it says if your V2 is 1.9, what we're saying is, all right, fine. If you decrease the temperature by 20 Kelvin, which is the same as decreasing by 20 degrees Celsius, then that means that it goes from 2.0 to 1.9 liters. Okay, so if you simply put 1.9 liters for your answer, that's also fine too, but I just put it this way to kind of hopefully make it a little clearer what it's representing. Okay, so let's get these things out of the way. Okay, so I've mentioned how to calculate Kelvin earlier because of this question. As a reminder, I'll go back to it again. Example problem 13-3. A sample of gas at 15 degrees Celsius and 1.00 atmospheres has a volume of 2.58 liters. The temperature is then raised and the volume expands to 3.04 liters with a pressure of 1.00 atm. What is the new temperature? So once again, one of the first things I'm going to say is you'll notice it says some things are changing. Temperature is raised, so the temperature changed. The volume expands. But the pressure starts at 1.00 atmospheres and ends at 1.00 atmospheres. So if the volume, if the pressure is not changing, then we ignore things that don't change if other stuff is changing. So ignore the parts that don't change if other stuff is changing. This is what's going to happen with these kinds of calculations. So I'm going to look at this and say, okay, temperature changes, volume changes. Reach back in my memory, pull out this equation, because don't expect this to be given. Don't expect any hints of what to use. Okay, so now given that, let's do this. Let's go ahead and plug in the numbers. Well, figure out what our units, what our variable is going to be, and then we can plug in numbers and solve. So let's see. Sample of gas at 15 degrees Celsius. Temperature is raised. New temperature. Temperature 2. And if that's temperature 2, this must be temperature 1. And it expands to this. So that's going to be our volume 2. And if that's our volume 2, then this is our volume 1. So we're trying to solve for T2. So the thing is, remember, because Celsius can go negative, you're not ever allowed to use Celsius in these calculations. It is absolutely required under every circumstance to use Kelvin. So let's get this out of the way. Maybe I'll leave these crossed out. remember, if you're given degrees Celsius, you have to add 273 to make it Kelvin. So just, in general, remember, Kelvin is always the bigger number. So if you have Kelvin, it should be a bigger number. If you have degrees, if you're trying to go to degrees Celsius from Kelvin, it should be a smaller number. So, okay. Conversion from degrees Celsius to Kelvin, this is what you use in the calculation. So identify what you're going to do. Solve for T2. So how do we solve for T2? Okay, you need to get T2 by itself. So you times both sides by T2. That'll get that like that. Now, did I animate the whole thing out? No, I didn't. Okay, I want to make sure everyone can see this. So now we have T2 V1 over T1 equals V2. Now we multiply both sides by T1. So those cancel. Now we have T2 V1 equals V2 T1. Now we divide both sides by V1. V1 cancels. T2 equals V2 T1 over V1. Okay, it's important to be careful with the algebra as you do it here. So anyway, there we go. That's the rearrangement of the equation. Here's the same deal right there. And then, once you've identified your variables, and then once you have rearranged your equation, now you can plug in your numbers and solve. And that's what it says right there, plug in numbers and solve. So we got your equation rearranged. Plug in the numbers right there. Liters cancel liters, you have Kelvin as your final answer, and your answer is 339 Kelvin. Now, you're partially there with this, because here's the thing. You're supposed to reply with the same units given. If it gives you degrees Celsius, you need to reply in degrees Celsius. That means take this Kelvin, and because degrees Celsius is always the smaller number, you subtract 273 to get this, your final answer. Now, the one thing that I haven't mentioned too much before is that significant figures are still an item to be considered. For example, back here, let me try and bring it up. 2 sig figs, 2 sig figs. Here with the volume, we also had 2 sig figs, 2 sig figs. However, with temperature, it gets to be a little messy with significant figures. So in terms of how it's going to go with significant figures, yes, one can say that technically a 3 sig fig answer should come out of here. And when you subtract, now you're counting decimal places, so a whole number generates a whole number. But in reality, with this, a lot of strange things can happen that are too complicated to go over right now with temperatures. But suffice to say, we're not going to worry about significant figures with temperature. We'll worry about trying to get it to a certain number of sig figs with temperatures. Just strange things can happen, so don't worry about it. All right, so having said that, here's other questions that can be practiced with, and strongly recommended. Pause now and do practice. All right, Guy-Lussac's law. French, I'm not sure exactly how you're supposed to say it, but Guy-Lussac. This one is going to be the same ideas as all the rest and derived the same way as all the rest. The guy noticed that when he compared pressure and temperature, the greater the temperature, the greater the pressure. You raise the temperature of something, more pressure. Okay, it's like if you heat up a soda bottle high enough, it's going to explode, or even a soda can. It'll explode. Greater temperature raises the pressure, lower temperature lowers the pressure. So what he did was he noticed that if you take the pressure at a certain temperature and do this, you get a constant that is the same no matter what you do with any other combination of pressure and temperature. Because if you lower the temperature, you get a lower pressure, and you do this, you get the same constant, even though it's different numbers. So because of that, if this is equal to the same thing that this is equal to, then they're equal to each other. So once again, that's how you get this thing, and this is the law you use. So it's the third law to keep an eye on. And this is going to be the sort of deal where you are going to be doing the exact same things again. Temperature in Kelvin, pressure using any of the units that we've talked about. So let's see. Let's go through an example question. So you're going to get this on the test. It won't tell you that this is a Guy-Lussac law question. So how do you know to use it? Okay, you look at what it gives you. Temperature, pressure, temperature. It mentions volume, but it says it's constant, which means if something's changing and this isn't, then if something's changing, we ignore the things that are not changing. So what that means is we got temperature and pressure. Okay. So you reach down into the recesses of your memory and think, what do I remember that involves temperature and pressure? That equation. Next, let's see, is heated to 50. So I'm reading this and decide what's P1, what's P2, what's V1, what's V2. So we say, pressure 1, pressure 2, volume 1, or temperature 1, temperature 2. It's heated to this temperature, which means it becomes this temperature, which means it's temperature 2. And if that's temperature 2, this must be temperature 1. The new pressure would be pressure 2, which means the original pressure is pressure 1. You could also say that because this goes with this, if that's temperature 1, it's pressure 1. So given that, the next step, identify your variables, done. Convert temperatures to Kelvin. Oh yeah, don't forget, you cannot do this temperature calculation with degrees Celsius. You will get the wrong answers. And then once you've done that, it's a matter of rearranging the equation for what you need. You're trying to find the new pressure, that's P2, which means we're going to multiply both sides by T2 in order to get P2 by itself. So T2 times P1 over T1. So there you go, T2 times P1 over T1. And then plug in the numbers with Kelvin canceling Kelvin to give a pressure in atmospheres. Okay, so I just put this here to be a little clearer for the viewer. If you were to box this on the test, fine. Notice with we ignore sig figs for the temperature, which means we just say 3 sig figs, 3 sig figs. Everyone's happy. All right, and so then based on that, all the rest of these can be solved in what amounts to essentially the same way. All right, let's get these out of the way. All right, that takes care of that.